Now that we are introduced to reference types, we are going to revise our typing rules to accommodate these reference types. And the idea is very simple. Recall the addition rule, which said, the original rule said that if E1 is of type int, E2 is of type int, then E1 plus E2 is of type int. So this was the original addition rule that we had discussed earlier. But now the revised addition rule would just generalize this to accommodate the subtyping relation for the reference type. It says if it is true that E1 is of type T1 and E2 is of type E2 and T1 is a subtype of int. So T1 could either be int or a subtype of int. Recall that int reference is a subtype of int, and T2 is a subtype of int. Then it is true that E1 plus E2 is of type int. Now there are two things to notice here. Number one is of course the generalization, where we are allowing T1 to be either int or its subtype. And the second thing here is that E1 plus E2 is necessarily the value type int, not the reference type int. And it's not any other subtype of int either. So what are the implications on what are the valid expressions that the language supports because of this typing rule? Well, here if I declare a variable int x, then x is of reference type int, and because of this rule, x plus 3 is a well-typed expression, right? So x plus 3 is a well-typed expression, and so this is a correct well-typed, it's a type correct expression because x is of type int reference, 3 is of type int, and so int reference gets pattern matched with T1, int gets pattern matched with T2, and E1 plus E2 gets pattern matched, is of type int, and so this whole expression is of type int if we use the sequence rule and the scope rule after that. Now let's take another example. Let's say x plus 3 colon equals 1. Now this is not well typed because x plus 3 is of type int by our typing rule, because when you use the addition operator you get an int type. But what you require in the LHS of an assignment operator, recall from the last module, is an int reference type, and so this is not a type correct expression based on our rules. So you can similarly generalize all our typing rules to accommodate reference types by just using the subtyping relation. Recall that a reference type is a subtype of the corresponding value type, and so if you just generalize it like this, you basically can accommodate reference types as it is, as though they were just if they're only the value is being used in the expression. All right, now let's go to another typing rule, which is the typing rule for a loop, the while construct in our language. So the while construct in our language looks like while some expression e, and then some other expression x, which forms the body of the while loop. So the idea being that if e is true, then x is executed, and after x has finished execution, you again evaluate e, and you keep doing this until e evaluates to false. If e never evaluates to false, then this becomes an infinite loop. If e evaluates to false on the very first check, then x is never executed. And so the question is, what is the type in our language? What type do we want to assign this expression while e x? All right, so here is a typing rule which gives a type to this expression. It says if e is of some type tb, x is of type t, and tb is a subtype of bool, then it is true that while ex is of type void. Now notice that first of all, I notice that e can be of type tb such that tb is a subtype of bools. For example, e can be of the bool reference type. This is a similar generalization that we saw on a previous slide. X can be of any arbitrary type t, and this expression here is of type void. Recall that void is a supertype of all other types, and there's no operation that is valid on a void type. This choice of using a void type for the whole while expression is interesting. One question that may arise in the mind is, well, if x is of type t, why not just give t as the type of the entire while loop? Well, the answer is, well, recall that the intended semantics of the while loop are that if E did not execute even once, then X is never executed. So if the intent was, if the intention here was that the value returned by this loop is the value returned by the last execution of the body, it is possible that the body never executed, and in which case it would be incorrect to say that this whole expression has type T. And so the choice that the language designer has made here, which is us, so the choice that we make as a language designer here is that we just give it a void type. So what does it mean? So for example, let's consider this expression while x is not equal to 10, x colon equals x plus 1. Well, this expression here will have the type void. Recall that this expression here will have the type int, and this expression here will have the type bool. But void cannot be used with the addition operator because there is no typing rule that basically allows me to add void to 1, and so this is not type correct, and because of this plus 1 at the end. Okay, now here's another rule for the address of operator, which is the ampersand operator found commonly in C and C++. So if it is true that x is a reference type T ampersand, then address of x or ampersand x in the programming language syntax is of type T star, or the pointer type to star. So for example, if x was a reference type int, then ampersand x is of type, this whole expression here would be of type int star. But notice, so this is type correct based on our address of rule in conjunction with the sequence rule and the scope rule. But what about ampersand 1? Well, ampersand 1 does not fit into this type rule because 1 is of type int, but what we require is that the operand of the ampersand operator, the address of operator, should be a reference type, and 1 is not a reference type, and so this is not type correct. All right, now let's come to our next construct of our language, which is the if then else operator. So we want to give a type to if E1 then E2 else E3. If it is true that E1 is of type TB, so that TB is a subtype of bool, and E2 is of type T2, and E3 is of type T3, then it is true that if E1 then E2 else E3 is of type void. Now once again, this is a choice that the programming language designer has made, just saying that this expression is of type void and not, for example, a type that is related to either T2 or T3. And once again, the implications of that is that whatever is the return value of this cannot be added to some other value, for example, or cannot be used with the logical AND operator, etc., because nothing can be used with the void operator. So let's see what kind of expressions this typing rule admits and what it rejects. So if 1 less than 2, then 4 else true. Now this basically, so 4 evaluates to int, true evaluates to bool, 1 is less than 2 evaluates to bool, and this whole expression therefore evaluates to void. And so far we have been able to type the whole expression, and so indeed this expression is type correct. What about this expression? If 1 is less than 2, then 4 else 5 plus 1. Now this expression here, based on our typing rules, will be of type void, and I cannot use the plus operator with the void type, and so this is not type correct. Notice that our language allows the then expression and the else expression to have different types, as seen in this example. All right, so before I move on to my next construct, I want to introduce this notion of the least upper bound of two types. And before I do that, I'll introduce upper bound. An upper bound U, represented by U equals UB, upper bound of two types S and T. Let S and T be two arbitrary types, then we say that U is an upper bound of S and T if the following holds. So U is an upper bound of S and T if and only if S is a subtype of U and T is a subtype of U. So both of these should hold, okay? So both of these should hold. All right. So for example, void is the upper bound of any two types T1 and T2, because T1 is always a subtype of void and T2 will always be a subtype of void, because void, recall, by design is a supertype of all other types in a language. And so void is the upper bound of, is an upper bound of any two types. Similarly, int is an upper bound of int and int ampersand, or int reference, because int is a subtype of int, reflexivity, and int ampersand is also a subtype of int, because every reference type is a subtype of its corresponding value type. Okay, so now that we understand what's an upper bound, so diagrammatically speaking, if I kind of draw my subtyping relation, the partial order, as in a diagram, then an upper bound basically represents, so let's say this was S and this was T, then all common ancestors of both S and T represent the upper bounds of S and T, and there could be multiple upper bounds for two types. There's a special upper bound called a least upper bound, which I'm calling L here, which is LUB of S comma T for two types S and T. LUB is such that L is an upper bound of S and T, so it is a common ancestor of S and T. And further, for any other upper bound U2 of S comma T, U2 should be a subtype of L. L is a subtype of U2. All right. So it is the least such upper bound. So it is the first common ancestor of S comma T. So once again, L is a least upper bound if it is an upper bound such that for any other upper bound, L is a subtype of U2. Okay. So first of all, what are some properties of least upper bound? In general, for any partially ordered set, like the set of types in our language, recall that our types can be thought of as a set, and the subtyping relation can be used to order that set. Because the subtyping relation is reflexive, transitive, and antisymmetric, this is also called a partially ordered set. And in general, the least upper bound for any two types need not be unique for a given partially ordered set, even in the presence of a void type, which is an upper bound for all other types. It's not necessary that LUB is unique for any arbitrary lattice or for any arbitrary poset or partially ordered set. But in our language, the language that we are discussing as an example, we are ensuring that it's always unique. And typically language designers will ensure that the typing, if they want to use the least upper bound operator in their typing rules, then they will ensure that the least upper bound is always unique. So we're going to use the LUB operator in our typing rules as we're going to see in the next slide. So let's see, what is the LUB of int and bool? Well, int is not a subtype of bool, neither is bool a subtype of int. What is the only upper bound of int and bool that we know? It's probably just void. Okay, and that's the only upper bound of int and bool, and so it's also the least upper bound of int and bool. What about LUB of int and int ampersand? Recall that int ampersand is a subtype of int, and int is also a subtype of int. So like there are two upper bounds of int and int ampersand. One of them is int, and another one is so another upper bound of int and int ampersand is void. Which one is the least upper bound? Well, because int is a subtype of void, this is the least upper bound. So the least upper bound of int and int ampersand is just int. All right, so now I come to my last construct in this module, which is the ternary operator, which is similar to the if-then-else operator, but it has slightly different meaning. So the syntax is E1 question mark E2 colon E3. This is similar to the ternary operator you'll find in C and C++. And the idea is you will check the value of E1. If it evaluates it true, then you return E2, else you return E3. The difference between if-then-else and the ternary operator is that this actually returns a value that can be used for further computation, as we're going to see in this typing rule as well. So this rule is called the ternary operator. And if it is true that E1 is of type TB, so that TB is a subtype of bool, and E2 is of type T2, and E3 is of type T3, then it's true that E1 question mark E2 colon E3 is of type least upper bound of T2 comma T3. And it's not just the least upper bound, but the value, the value type of the least upper bound of T2 comma T3. So recall that for the if then else operator, we were basically saying that it is a void type, but for the ternary operator, we are actually giving a more precise type, a type that can be used in more operations. So for example, let's look at some examples to understand what this typing rule admits and rejects. So is X question mark Y colon Z colon equals 10 a valid expression? Well, Y and Z could be reference types, but X question mark Y colon Z is definitely a value type because we are saying that the value type will only be returned by this expression. And we recall that the LHS of an expression of an assignment statement should always be a reference type, and so this cannot be a well-typed expression ever. All right, let's take another example. If 1 is less than 2 question mark F5 colon 4 plus 3. So 5 is of type int, 4 is of type int. So this whole expression, 1 is less than 2 is of type bool. So this pattern matches with TB. And this whole expression is of type LUB of int comma int, which is just int. And int plus 3, so 3 is also int. So int plus int is well typed, and so this is a well typed expression. All right, let's take another example. 1 is less than 2 question mark 5 colon true. Now 1 is less than 2 is boolean, so that matches with TB. 5 is int, true is bool, and so int matches with T2, true matches with T3, and so the type of this expression would be val of LUB of int comma bool, which is just void. And so this is also a well-typed expression because our typing rules evaluate a type for it. It's a type correct expression.